This is recitation 12, and today we will solve two problems. One on LC circuit and one on displacement current. So this will be problem 1. For problem 1, we have LC circuit. We have a capacitor and we have an inductor with inductance L, capacitor with capacitance C. At time moment 0, I have charge at the plates of the capacitor equal to Q naught. So the capacitor was charged. Then I had current at time moment 0. That was 0. And those are our initial conditions. At time moment 0, I close the switch and we have current in our circuit. So we need to make some decisions. I will choose plus Q, charge on the upper plate of this capacitor, minus Q, charge on the lower plate of the capacitor. Then when I close the switch, there will be current. Which direction of current do we choose? I will choose clockwise direction. You can choose counterclockwise. I choose clockwise direction of current. Now what we are looking for? We are looking for the charge as a function of time. Let's find charge on the plates of the capacitor as a function of time. Which law will we use? We will use Faraday's law that tells us that integral E dot dr over closed path is equal to minus d dt of changing flux of the magnetic field, integral B dot ds. So I follow the steps. I have my charges on the plates of the capacitor. I have direction of current. Now I need to indicate which way will I go around the loop. I will go around the loop in the counterclockwise direction. This is my choice. ds, if I go around the loop in the counterclockwise direction, then ds is out of the page. Now I will be working with the right-hand side of Faraday's law. Integral B dot ds, we call it phi, flux. Flux of the magnetic field is plus minus Li. Which sign do we choose, plus or minus? I have current in clockwise direction. If I have current in clockwise direction, you need to use your right hand to figure out what will be the direction of self-induced magnetic field. Ironically, I use my left hand because you see my mirrored image. So you use your right hand, you follow the current with your fingers, you bend your fingers along the current, and your thumb shows the direction of the magnetic field. So the magnetic field in this case is into the page. Self-induced magnetic field is into the page. I will put it right here. B self is into the page. So B self is into the page, ds is out, B dot ds dot product is negative. That's why I choose minus. Phi is minus Li. Next step is to find d phi dt. d phi dt is minus, L is constant, di dt. Now we are ready to work with the left-hand side of Faraday's law. I go around the loop in counterclockwise direction. We have the capacitor here. When we go through the capacitor, what is the voltage change? Or in our case, what is change of E dot dr? The electric field is down. dr, since we go in the counterclockwise direction, dr is down. So electric field is parallel to dr. That's why dot product E dot dr is positive. I put plus. And the magnitude of E dot dr across the capacitor is Q over C. Let me use a different color to write it down. So it is plus Q over C. Then this is E dot dr. This is equal to minus from Faraday's law, minus, and then d phi dt, and d phi dt is minus L di dt. Minus minus plus, so I have L di dt. And now we are ready to write our final equation, except for one thing. Look, we have charge and we have current. We need to relate charge and current to have one equation and one unknown variable. Current is plus minus dq dt. Which sign do we choose? Plus or minus? With our notations, the current is leaving positively charged plate of the capacitor, so charge decreases. Derivative of charge is negative. That's why I choose negative. It is minus dq dt. Minus dq dt. And now I'm ready to write our equation. Let me do it right here. I bring current in my equation. I have Q over C on the left, and it is equal to L, and di dt is equal to minus d2q by dt squared. So it is L minus d2q by dt squared. And then I bring this guy to the left, and it comes with plus, so I have L d2q by dt squared plus 1 over cq, and this is equal to 0. Now look what I will do. I will divide each of these guys by L. Why? Just I want to do that. Then what do we get? d2q by dt squared plus 1 over LCQ, and this is equal to 0. Now look at this equation. Do you recognize it? It is the equation for harmonic oscillator that we studied in our mechanics class. Second derivative with respect to time, then constant, then the variable itself, and this is equal to 0. So how do we solve this equation? Let's solve it. Let's find Q as a function of time. We will be looking for the solution of this equation, Q, as a function of time, as unknown constant A, cosine omega t, where omega is unknown, plus B, sine omega t. B is unknown and omega is unknown. Why am I doing that? Look at this equation. It's a reasonable guess because I have second derivative plus function itself, and it is 0. So cosine and sine is a reasonable guess to look for the solution. What I will do next, I will apply our initial conditions to find A and B. So we find A and B from initial conditions. Q as a function, Q at time moment 0, Q at time moment 0, let's plug in time moment 0. T0 cosine 0 is 1, so I have A, then plus B, sine 0 is 0, that's it, I have A. And we are given that Q at time moment 0 was equal to Q naught, the capacitor was charged. Now we need to apply the second initial condition, and I need current. I remind you that current is minus dq dt. Minus dq dt. I keep minus, and then let's differentiate dq dt. What do we get? We get A. Derivative of cosine is minus sine omega t. Chain rule will give me omega. We are done with the first guy. And then the second guy, plus b, derivative of sine is cosine omega t, cosine omega t. And then chain rule, I apply chain rule, and I have omega here. This is I, current, and now I apply the initial condition. Current at time moment 0. Time moment 0, sine 0 is 0, cosine 0 is 1, so I have minus b omega, and current at time moment 0 was 0. So b is 0. We found A and B. So now I can rewrite my solution. I know already that B is 0, and I can rewrite my guess. What we need to do next, we need to find omega. Q as a function of time now is A, which is Q naught, times cosine omega t. How to find omega? I take my guess and I plug it in my equation. I have second derivative, d2q by dt squared. What is the second derivative? The first derivative. Let's do it again. dq dt. What is dq dt? It is q naught. Derivative of cosine is minus sine, sine omega t. And chain rule gives me omega. Now the second derivative, d2q by dt squared, is equal to minus q naught. Derivative of sine is cosine omega t, and the chain rule gives me omega. And I already had omega, so I missed this omega. I'm sorry. So 1 omega was here, chain rule gives me another omega, so I have omega squared. Now this is d2q by dt squared, and I'm ready to bring it back to into my equation. So I have minus q naught, omega squared, cosine omega t. This is d2q by dt squared, plus 1 over LC. Q is q naught cosine omega t, and this is equal to 0. Now I divide both sides of this equation by cosine omega t. I divide both sides of this equation by q naught, and what we get is minus omega squared plus 1 over LC is 0. Which means that omega squared is 1 over LC. Omega squared is 1 over LC. So now we know A, we know B, and we know omega. We found the solution. I will erase the equation, and we will write our final solution. My final solution for the charge as a function of time, Q as a function of time, is Q naught times cosine. Omega is 1 over square root LC times time. This is the charge as a function of time on the plates of the capacitor. And we see that this charge oscillates. So if we start with a positive charge on the upper plate of the capacitor, with time it will become negative, and the low plate will get the positive charge. So we will have oscillating solution for the charge as a function of time.